Hi everybody, welcome back. This is Professor Marinos, and today we're going to begin our lecture on thermodynamics. Thermodynamics is one of the key concepts in geochemistry, and what it does for us is it allows us to define what are possible chemical reactions versus impossible chemical reactions given an environmental system. So for instance, why can a fire burn wood and produce carbon dioxide and water from that wood? But if you combine carbon dioxide and water into an atmosphere together, you never produce a piece of wood that you can hold in your hand. And a key concept in thermodynamics is the idea of an equilibrium, which is the topic of this video today. Now, I know a lot of you have had exposure to thermodynamics in your high school and college level general chemistry courses, but since it's such a foundational principle of geochemistry, this module is meant to be as a refresher and to build on that previous material so we have a solid foundation in thermodynamics moving forward. First, let's go through our overall module learning objectives. By the conclusion of this module, you will be able to describe what a system is and how it's delineated, explain why the laws of thermodynamics dictate that a chemical system always moves towards equilibrium, and finally, you'll be able to predict whether simple chemical systems are at equilibrium, and if they're not, predict the direction that the reactions will proceed in order to bring these systems into equilibrium. For this particular video, the learning objective is for you to be able, by the end of the video, to give a plain language definition of what an equilibrium is. So let's jump into that. So what is equilibrium? Well, there's a popular definition of the term suggesting inner harmony or harmony with one's environment. And this isn't too far off from the scientific definition of the term. And we can break down the word into its components to consider what the word might mean. So if you take equilibrium, equa means equal, and librium means balance in Latin. And you might also recognize this from the zodiac sign Libra, which is a scale. And so the term suggests that things are in equal balance with each other. And a key point in this conception of equilibrium being a state of equal balance is that it is also a state of rest. That is, that there's no net change occurring. And in thermodynamics, a central point is that systems are always moving towards this state of rest. Perhaps unlike you or I in our mental states, chemical systems always proceed towards a state of equilibrium. Now, what does it mean for a chemical system to be in a state of equilibrium? That means that there's a balance between the reactants and the products in a reaction. This doesn't mean that they occur in equal amounts any more than putting an elephant and a beach ball on a scale will result in them balancing. But the central question of thermodynamics is identifying the point at which both the reactants and the products balance each other in a chemical system. Because of this conception of equilibrium as a point of rest for a chemical system, a common visual metaphor that's used to explore equilibrium is the idea of a ball in a series of hills and valleys as shown here. And the equilibrium point of a system is where this ball reaches its lowest point of rest, indicated here. And the central idea of thermodynamics is to identify this place of rest in this system such that you can look at other systems that aren't in equilibrium, such as this red and this blue ball here, and identify which way the systems will move to attain this state of equilibrium. And indeed, you need not know anything about the shape of the hills and valleys between the systems in disequilibrium and the systems in equilibrium to know the direction that they're going to move. All you have to know is that for the blue ball, for instance, the equilibrium point is to the left, and for the red ball, the equilibrium point is to the right. And as we move through this lecture, we'll understand a little bit more what both this x-axis and this y-axis mean. So what do the heights of these balls mean, and what do the directions mean in this metaphor? Now, an important thing to recognize is that thermodynamics can tell us the direction that a reaction is going to proceed in. It can't tell us anything, however, about the speed that reactions are going to proceed in. That topic, the speed of reactions, is the domain of kinetics, which is a separate field that we'll discuss later as well in depth. So I hope I've impressed upon you the importance of chemical equilibria and thermodynamics to your overall understanding of geochemistry. But today I'm going to leave you with a story of when chemical equilibria had a dramatic and long-lasting impact on the health and well-being of people. And this story is the Flint water crisis of 2014, which occurred in Flint, Michigan. And I'm sure many of you are familiar with the Flint water crisis, but perhaps did not understand the chemistry behind it. So, the city of Flint, like many cities in America, has its water delivery system flow through lead pipes. And this is a result of development of these cities in the early part of the 20th century, when the negative health impacts of lead weren't particularly well appreciated. Those impacts obviously are well appreciated nowadays, though, and as a result, water managers in cities aggressively modify the chemistry of water such that there is an equilibrium between dissolved minerals and solid minerals on the insides of pipes that promotes the formation of a mineral crust lining pipes. And this crust acts as a protective barrier between water and these lead pipes that prevents the transmission of lead into the water supply. Flint initially received its water from the city of Detroit, and the people in Detroit did manage the chemistry of the water to promote the formation of these crusts on the insides of pipes. But in 2014, as a cost-saving measure, the city of Flint changed its water supply to the Flint River, but they did not adequately modify the chemistry to keep these crusts in place. As a result, the equilibrium between dissolved minerals and deposited minerals shifted such that when the chemical system moved to restore equilibrium, these crusts dissolved from the walls of the pipes, eventually directly exposing drinking water to the lead pipes, causing massive lead poisoning, with lead levels in drinking water between 10 and 1,000 times what the EPA recommends for drinking water consumption. And this is all brought to light by an environmental activist, Leanne Walters, who sampled her drinking water and found lead in it, and then subsequently sampled her neighbors and then hundreds upon hundreds of other Flint residents, and brought it to the attention of both water managers and some scientists at Virginia Tech. You can read a bit more about this in the popular science article I cite below. In these next few videos, we're going to explore first, what do we mean by a system, particularly what do we mean by a chemical system. We're going to provide a rigorous definition for that, and then we're going to move on to the laws of thermodynamics, which describe where equilibriums will occur in chemical systems. Thank you for listening.